So our lecture today is going to have two parts. First part is going to be about how to apply the ideas of linear momentum that we have been studying over the past few weeks or few lectures. How to apply that to the more complex problem of collisions in two dimensions. That's the first thing we are going to be studying today. Let me try to illustrate that for you. This first part. We will have a second part where we are going to start introducing the notion of rotational motion. So two very distinct parts in this lecture today. Let's think about the first part. What is going to be the main idea on the first part? Linear momentum and collisions in two dimensions. Here's a cartoon. Here's at the bottom a cartoon of a type of collision that we've studied very well recently. These are collisions in one dimension. You see, this mass, this object, is moving along the, say, x direction. And this other object, which was at rest, there's this collision, but everything is happening in just one dimension. Now, when the particles separate, they actually go out in that same dimension. So this is a problem restricted to just one direction of motion. Now, what we are going to introduce today is something a little more spacious. We've been thinking about billiards in the context of the one-dimensional collision, but you guys actually know that in real billiards, things are happening on a table. So we actually have a two-dimensional collision. Imagine here a billiard that is at rest, and the other billiard comes and hits it at a glance. So one billiard goes in this direction, the one that was at rest goes up this way, the other one that was moving goes into, say, to the right. This one goes to the left. And we are talking about here the x and y plane. So this is a little more involved problem because linear momentum is a vector. We actually have to impose the idea of conservation to the vectors, not to just the magnitudes of these objects. So we actually have to apply this to in a more vectorial way, if you will. So this is the idea of what we're going to study on part 1 of this lecture. Okay? So after we analyze that, we're going to move to a part 2, which is actually very important. It's the idea of introducing some new concepts about rotational motion. What's going to happen when we introduce rotational motion? Let me give you this general overview of what the second part is going to be. There are lots of things in nature, and I put this picture here. Think about the wheel of a car. It's actually rotating. Here's a picture of a ballerina. She's rotating. Here's a diver, also rotating. Look, a propeller of an airplane. A little toy like a merry-go-round on a playground with children on it. You know, think about something as complicated as planet Earth or as large as planet Earth. It is also a rotating object. So rotations is a type of phenomenon that is present all over the place in natural systems and also in engineered systems. We have to understand how to deal with rotations. We're going to just do an introduction today, but you will begin to appreciate that. Let me tell you some of the new ideas that are going to be coming up in our study today. Truly new ideas that we haven't learned yet. Look, just like we did the kinematics of motion in one dimension and kinematics of motion in 3 dimensions as far as translation goes, now we have to talk about rotation. How do we study rotation? We did study a preliminary problem that dealt with rotation, which was the circular motion. Guess what? We're going to bring the idea of an angle to talk about angular motion. There's going to be a concept we're going to introduce called the rotational inertia. Just like objects moving, undergoing translation have inertia, there is also the equivalent for rotational motion. We call it rotational inertia. Look at this. You're very familiar with something called kinetic energy of translation. We're now going to introduce the kinetic energy of rotation. We've discussed the linear momentum. We are now going to bring in a concept that we'll call angular momentum. And finally, just like we talked about conservation of linear momentum, we're also going to bring the conservation of angular momentum. So there will be some new ideas, okay? So this is going to be our second part of this lecture. We'll be talking about an introduction to rotational motion. Again, two parts we have to deal with today. First part, let's go back to it. We have studied the essence of linear momentum, and that essence is illustrated in this, is summarized in this page here, right? Linear momentum is this quantity we invented, which is basically the velocity of the particle times its mass. It's particularly useful because when the net force on the particle is zero, we can think of the linear momentum as being a conserved quantity. This has all its power when we analyze a system of n particles that are interacting. We can invent there the total linear momentum, which is the sum of the individual linear momentum, the linear momentum of each of the particles. If we add those, we get the linear momentum of the system. In the case of the external force being zero, the linear momentum of the individual particles may change, but the linear momentum of the total system, the total linear momentum, is actually conserved. It's a very helpful idea. We also introduced the position of the center of mass, the velocity of the center of mass, and the acceleration of the center of mass. When the external force is zero, this Newton's law implies that the acceleration of the center of mass is also zero, meaning the velocity of the center of mass remains constant. These are very powerful ideas in the area of linear momentum. We can apply these ideas to the notion of collisions. We studied the case of a completely inelastic collision. Inelastic collisions are those in which the mechanical energy is not conserved. We studied this case in which, you see, when the particles collide and they stick, this is obviously requires some conversion of that energy, mechanical energy, into thermal energy. And so even though the mechanical energy is not conserved, the linear momentum of the system is conserved. So you can study, if you take the linear momentum in the beginning, it has to be equal to the linear momentum at the end. That allows us to predict the final velocity. Now, in the case of an elastic collision, if the collision is such that the mechanical energy is conserved in addition to the linear momentum being conserved, we have a collision in which that we call elastic. Sometimes people call this a perfectly elastic collision. Basically it means that the kinetic energy after is equal to the kinetic energy before. So these are collisions in one dimension, and we have studied them quite a bit. Now, it gets more interesting when we transport this idea of collisions, when we transport it to the sense of when things are happening in two dimensions. And this is really what happens on a pool table, right? Imagine this is a billiard that is at rest. Here comes another billiard that doesn't hit it head on. It hits at a glance, something like a glancing collision. You know what's going to happen. This ball that was at rest is going to go in one direction, while the other ball that came in is going to go into the other direction. Now, because this system may be understood as an isolated system, right? Because on the table, on the pool table, what do you have on the pool table? The friction with the pool table, it's in an ideal situation, you can neglect that. And gravity doesn't play a role because gravity's pulling the balls down, whereas the table exerts normal. So you can think of this system, the pool table, as the balls actually only having, of course, when they collide with the edges of the pool table, then you have external forces there. But let's think of just two balls far away from the walls of the billiard, the perimeter of the billiard table, the pool table. When these balls collide just between them, you can consider them as an isolated system. If the system is isolated, the linear momentum of this system will be conserved. Now, how do we analyze this problem? We have to apply then, because the problem is in two dimensions, we have to apply the conservation of linear momentum. Along both of the axes, we have to apply conservation of linear momentum along the x-axis, and we have to apply conservation of linear momentum along the y-axis. Now, if the collision is elastic, like an outstanding pool table, and the balls are very smooth and very nice, like a pristine new table, professional grade, you can approximate that the collisions will also be elastic, meaning the kinetic energy in the beginning will be equal to the kinetic energy at the end. There's conservation of mechanical energy, no energy lost to heat or friction, or due to friction, or even sound, right? We know that this is an idealization, but let's say that we can use this idealization here and think that the collisions are elastic. So in that case, we can apply both conservation of linear momentum and conservation of mechanical energy. I'm going to put here an equation that seems complex, right? It seems complicated, but this equation is actually the equation that indicates conservation of linear momentum along the x direction. Let us analyze that. What do we have on this side of the equality? This is the linear momentum of the system in the beginning. That was before the collision. That's why we call the I here, you see? What is m1? m1 is the mass of this particle. What is v1i? It's the speed of this particle, right? It's the magnitude of the velocity of the particle. So if you take m1 multiplied by the velocity of the particle initially, this is the linear momentum that the system had in the very beginning. In the very beginning, this particle, this billiard, is supposed to be at rest in our construction here, which means there is no linear momentum there. That's why this is the initial linear momentum. Now, what is on the right-hand side of the equality? These are the component. These two terms represent the linear momentum of the particles after the collision. Let's analyze that. Look, what is this? m1 v1f. Look at that. Take this mass, which is m1, times v1f. That would be, the linear momentum of this particle. But we are now looking just at the x component of that. If you multiply by the cosine of angle theta 1, which we don't know what that angle is a priori, if you multiply that magnitude by the cosine of theta 1, that would be the x component of the linear momentum of particle 1 after collision. By the same token, look, m2 times v2f, which is the velocity, the final velocity of particle 2, multiplied by the cosine of theta 2, it gives the cosine of theta 2 will give the component of that v2f along the x direction. So you see, this is the x component of the linear momentum of particle 2, and this is the x component of the linear momentum of particle 1, both after the collision, because you see, this is after the stuff happened. This is the picture of the particle after the collision. This is the picture of the particle also after the collision. Very good. So this is one equation. This is what I'm talking about here. See, apply the conservation of linear momentum along each axis. This is along the x-axis. Now we have to do the same thing along the y-axis. Check this out. Here it is. Notice that the linear momentum, the initial linear momentum along the y-axis, it would be 0 in this construction because we chose the x-axis to be along the direction of the initial velocity. Notice that particle 1 has no vertical velocity, has no component of velocity along the vertical. That's why I say 0 for the initial linear momentum. So, what are these other two terms on the right-hand side? They are the linear momenta of the two particles after the collision. Obviously, they have to add to 0 in order to conserve linear momentum along the y direction. So you see, when you apply conservation of linear momentum in 2 dimensions, you have 2 equations, one for each direction. Okay? So, check this out. Let's look at what this is, right? If I have m1 v1 sine of theta 1, I will actually be getting the component of the velocity v1f times m1 along the y direction. I know this has to be a negative number, right? It has to be negative because it's in the negative part of the y-axis. On the other hand, I know that the component of v2f, when I do v2f m2 sine of theta 2, it has to be a positive number. One has to be positive, the other one has to be negative. I'm using angles theta here that are both positive and both less than 90 degrees, right? So when I add these guys together, I have to get 0. This is an equation for the conservation of linear momentum along the y direction. This is how this is done, okay? I'll let you take that in. All that we have done here is to apply conservation of linear momentum along the x-axis and along the y-axis. You have to be able to write these 2 equations yourself when you are looking at these billiards, right? Realize this is billiard before collision. This is billiard before collision. And these 2 are the billiards after the collision. See? V1f, V2f. So, now, imagine that you can, this equation, this equation is a complicated equation. There are several unknowns here, right? There's several unknowns. If you knew the mass m1 and if you knew the velocity v1, and if you measured both angles and you knew m2, then you can predict these 2 velocities because you would have 2 unknowns and 2 equations, right? Look, 1, 2, 3, 4, 5, 6, 7 numbers. There's 7 numbers in these 2 equations, right? The 2 masses, the magnitude of these 2 velocities, the magnitude of that velocity plus the 2 angles. There are 7 unknowns and 2 equations. If you give 5 numbers, you can find the other 2. That's it. That's all you can do with this algebra, right? Now, if in addition to this, you can say that the energy is conserved, that the collision is elastic, you get one more equation. It would be the equation for conservation of mechanical energy. Look at that. The initial kinetic energy, half of m1 v1i squared, equal to the sum of the kinetic energies of the other 2 particles. Look, this is the kinetic energy of the first particle, kinetic energy of the second particle. So if you are able to write this, then you have another equation. So you can actually have 3 unknowns, and you can find them all, 3 unknowns, but there are 7 total, so you still need to give four things, right? Notice that this equation for energy is a scalar equation. There is no angle here because energy is not a vector, right? It's a scalar, so this equation is a little simpler. These 2 equations came from the conservation of the linear momentum, which is a vector quantity. Okay? Now, with these 3 equations, that's basically the essence of what you need to solve any problem of collisions in 2 dimensions. And let me show you 2 examples that are going to come up in your assignments. Look at this lovely problem. It's a typical problem. Look, it's exactly the same setup, right? It's a different cartoon. Look, you have 2 ice pucks. One of them is at rest. They have equal masses, right? And they are involved in a perfectly elastic glancing collision. You see, mechanical energy is going to be conserved. And you see, you're given the initial velocity of this guy, and then this angle theta is 36 degrees. You have the other angle is 54 degrees. And so you're asked, what is going to be the final velocity of this guy and the final velocity of that guy? This is a very typical problem where you have to deploy these 3 equations we were talking about. So you have to, find what you know, what you don't know, and, plug it in, do the algebra, and you should be able to find the velocities. How does that sound? Okay? This is a problem you're gonna have a chance to do this, in your one of your next assignments. Look out for this problem. This is the idea. Critical thing here, remember, you can only use this 3rd equation when the collision is elastic. And here to leave no doubt, this is a perfectly elastic, meaning mechanical energy is really conserved. Conservation of linear momentum you can always use as long as you can assume the system is isolated. There are no external forces. And here you see pucks, ice pucks. No friction with the outside, normal and gravity cancel. This is a situation the external force is 0. Okay? So take that in. It's a very interesting problem to solve and to attack. Algebraically, it's a little complex, but you can do it, I'm sure. Now, here's another problem. This is a little more involved. Again, it's a similar thing. You have puck 1 coming from this direction, puck 2 coming from the other direction. And look at that. They collide and they go out like this, 40 degrees and 40 degrees. But there's a difference in this case. You see, this is not an elastic collision. This is actually inelastic collision because you see this puck gets smashed, gets deformed. Deformation usually leads to the loss of kinetic energy. Look what they say here. 16.8% of the initial kinetic energy of the pucks is lost. So look at that. You can still use these 2 equations because linear momentum is going to be conserved because the system is isolated. But this one you cannot use because the kinetic energy initially is going to be different than the kinetic energy at the end. You cannot use it. But there is a very similar equation you can use by writing down in mathematical form what it said in this statement. You see, 16.8% of your kinetic energy is lost. So you have to write this term, You have to write this term, subtract 16.8% of it, and then make it equal to the other part. I'm not going to write it because that's your job, but that's the idea. You have to mathematize in this way. And then when you solve this, there's going to be some unknowns, some things are going to be known, and you can determine the speed of the two pucks after the collision. All right? So this is the idea about this area of linear momentum applied to collisions in two dimensions. So that concludes the first part of our discussion today, right? And we're now going to begin moving into the second part. Let's talk about the rotations now. Rotations. Basically, here's a very busy slide that contains a lot of information about rotations, right? In a sense, we have already studied rotations when we studied the uniform circular motion. There is a lecture on this, an additional lecture recorded on this, and a particle undergoing circular motion is effectively rotating about the origin of the Cartesian coordinate system. And what are the essential things that we learn about rotational motion? Here's a very important idea about the rotational motion. We learned that the linear velocity, right? Compare these two places. Here we have the cartoon for the rotational motion, and here we have this expression. We learned that this the magnitude of the velocity of the particle, something that is called often the linear velocity of the particle doing circular motion, is related to the angular velocity, omega. What is the angular velocity? Omega is d theta dt, is the time rate of change of the angle theta of the particle doing the circular motion. That angular velocity, d theta dt, is equal to the linear velocity, dr dt, which is is related by this radius r. So the angular velocity times r is actually equal to the linear velocity. They are not equal, they are related. When you multiply the angular velocity by r, that has to be equal to the linear velocity. So this is a very important idea. Notice that the angular velocity, if you change the radius of a disk, this is something that's going to be very important very soon. If you have a disk that is rotating, all the particles in the disk are actually doing circular motion. So even though the angular velocity of all points is the same, particles that are farther out in the disk will have a greater linear velocity because their radii compared to the center of the disk are greater. Very important relationship in understanding rotational motion, how to link the linear velocity with the angular velocity. Okay, that's an idea that we're going to invoke very soon. Now, here's another idea that we also developed, this idea of the so-called centripetal acceleration. Sometimes we call the centripetal acceleration a sub r because it's a radial acceleration. The centripetal acceleration, which is here indicated by blue, this centripetal acceleration, the magnitude of it is the linear velocity squared divided by the radius. If you plug in this v in here, v is omega r. If you put omega r here, you can see that another expression for the centripetal acceleration is omega squared r. So this is another expression that is important when we are studying rotations. And finally, here's something also important. Even though you always have a radial or a centripetal component of the acceleration for something rotating, if the magnitude of the velocity increases or decreases, that's because there is a tangential acceleration. that tangential acceleration would be related to the magnitude of this linear velocity by simply taking a derivative. You see, when you take the derivative of the velocity, you get the tangential acceleration. If the radius is constant, the derivative of the omega is this alpha, which is the so-called the angular acceleration. These are important things. This AT is 0 when you have uniform circular motion, when this v is constant. But in general, if v is changing, if the magnitude of the velocity is changing, you're going to have a tangential acceleration. So this is another important relationship in the study of rotational motion. So you see, these three expressions, they will come back. They are related to the kinematics of the rotational motion. What is kinematics? It's how we describe motion. We describe angular motion, rotational motion using theta as a function of time. The derivative of that is the omega. That relates to the linear velocity by omega r. The acceleration associated with the linear velocity is the tangential acceleration. And the centripetal acceleration, centripetal component, is v squared over r. So these are important things that we have to learn how to use a little bit. They will come back to us. We're just doing this by way of introduction. Now, here is the big cartoon of the circular motion that we have described in detail. I'm bringing that up because if you do not understand what we are doing here, it will be impossible for you to understand rotational motion. So I encourage you to go back to that video lecture where we describe very well in detail how the position vector can be written as this radial vector, the magnitude of it, cosine theta along the x direction, and r sine theta along the y direction. When you take the second derivative, you actually obtain an acceleration that is clearly centripetal. See, this guy over here is again the radial vector, and you, because of the second derivative of cosine and sine, you get a negative number when you do the second derivative. You obtain this negative, which means the acceleration is in the opposite direction of the unit vector r. I'm going very quickly. If you're not understanding, it's because you have to go and look back at that video lecture that we did. So there's the centripetal force that pulls objects to the center, and that's the centripetal acceleration. This centripetal acceleration is what you get when the motion is uniform, when this velocity is constant, you see? But if this velocity changes in magnitude, in addition to the centripetal acceleration, there's going to be the tangential acceleration. You can think of this like this. You see, if you're driving your car and the speedometer shows a fixed speed, you're doing uniform circular motion. Your speed is fixed. There is no tangential acceleration, only radial acceleration, which is the centripetal. But if you step on the gas pedal while you're doing the curve, you're going to see the speedometer go up. That means there is a tangential acceleration. Your velocity is increasing. So in addition to the centripetal, there could be a tangential acceleration. Okay? So these are important ideas as we move into rotation. Look, another way to look at it, how to relate linear and angular variables. When we're doing rotation, we're going to be talking about angular variables, right? Look, if you have an angle, what is the definition of an angle in radians? Definition of an angle is simply s divided by the radius. Maybe I can draw here a little bit. Look, if you have a particle going through an arc, see, particle moves from this point to this point in a type of arc motion, which is the essence of a rotation, right? If this is the radius r, from here, the origin, to where the particle is, if this is the radius r, and this arc is the arc s, the angle theta in radians is defined. It is a quantity that we invented. The radius, the angle theta, is nothing else than s, this length, divided by r. Sorry, I'm writing like a first grader here, or even preschooler, but that's basically the idea. And you see, look, if you multiply theta by r, you get s. So that's how you relate the angle theta, an angular coordinate, with a spatial coordinate, with is an arc. This is basically, what you do when you're talking about angular position and linear position. Now, if you take the derivative of this, what do you get? You actually get the relationship that we talked about between s and omega, right? What is omega? Omega is d theta dt. And what is v? V is ds dt. So you take the derivative here, you take the derivative here, you actually get the relationship between omega and v. And r is supposed to be a constant number when we are thinking about a sector of a radial travel, right? Here's another thing that is going to show up when we think about circular motion. It's the idea of the period of a rotational motion. If you go back to the original position, you actually do a 2 pi angle, and if you divide that by the angular velocity, you actually get the time it takes to complete a full oscillation, right? So this is another important idea that we should consider. Now, what is the other thing that we were talking about here? If you take another derivative of v, another derivative of omega, what do you find? You find this expression. This is the tangential acceleration, and this is the angular acceleration. Is a further derivative, the tangential acceleration. Look, if you look at this cartoon is interesting, right? Because it's trying to represent here. Look at this. This is an object. It's an object that is rotating about a fixed axis of rotation. So if you look at that, this object that is large, it is rotating about a let's go over there and show it again. You see this large object? It is rotating about this fixed axis. Observe this point P. This point P is a point on the object. As the object as a whole rotates about this fixed axis, that point P is actually performing a circular motion. That's why circular motion is very important when you're studying rotations, because objects doing rotation about a fixed axis, their points are performing circular motion. And so, just like we had analyzed here, look at this object undergoing circular motion. All the points in a body that is rotating about a fixed axis they are actually undergoing circular motion. And you see, this is the velocity. Check this out. This vector is the velocity vector of that point. If that velocity vector increases in size, that means there is a tangential acceleration. The object may be increasing in its angular speed. It's covering greater angles per unit time. That would correspond to an angular acceleration, which is this guy over here. If the object is rotating with a constant omega, a constant angular speed, then that point is performing a uniform circular motion, and then the only thing that exists is the centripetal or radial acceleration, which points like this. And so you see, look at this cartoon down here. You see, it's trying to represent, for every point, there are two components of acceleration, the radial and the tangential. Now, the tangential may be zero if the object is rotating with constant angular speed. But if it is increasing its angular speed, then the tangential is not zero. The centripetal is always non-zero. The centripetal is always going to be there if the object is rotating, because the direction of the velocity needs to change. But if the magnitude of velocity doesn't change, that means the tangential is zero. I'm saying many things. You need to say these things to yourself and reflect on this. This is also a discussion that is very well described in the textbook, right? Okay. Now, this slide is going to try to compare for you things that we learned in linear translational motion with things that we're going to introduce now in angular motion. Look, we studied this equation. You're going to recognize it, right? This equation is the equation for velocity in a motion with constant acceleration. See, if you have a motion with constant acceleration, the velocity increases like this, linearly with time. Well, you can also have an angular motion where the angular velocity will increase linearly with time. And this is going to happen in this case when the angular acceleration is constant. So there is a correspondence between linear translational motion and angular rotational motion. There are analogous equations. Look, this is an equation for position along linear direction, translational position, quadratic on time. If there is angular acceleration, there is also an equation for the angle that is quadratic on time. You see, there is an analogy here. This analogy may be helpful sometimes to understand these two types of motion, how translational motion relates to rotational motion. Now, so these are some considerations, introductory considerations about kinematics of rotational motion, right? Now, let me start introducing to you a little bit about the energetics of motion. Many of the considerations we used when we studied translational motion they can be translated into the idea, the realm of rotational motion as well. One thing I'm going to introduce to you now is the kinetic energy of rotation. Just like there is the kinetic energy of translation, there is also the kinetic energy of rotation. Let me introduce this idea to you. Imagine a rigid body. What is a rigid body? A rigid body is a body that cannot change shape. Okay, it's like, something like a pen, like this. See, this cannot change shape. If it's rotating, its shape is actually preserved. There are many things like that. Let me look for another nice pen here. Look at that. The shape doesn't change as it is rotating. This is a rigid body. So, in general, different points on this rigid body, they have different linear velocities, see? Because you see, as this thing is rotating, this point is covering greater distances than this point in the middle, near the middle. So, this covers a great distance in the same time that this covers a small distance. So, the linear velocities are different. But all the points have the same angular velocity in a rigid body that is rotating. So, let me let me explain to you what we can introduce here. We can think about a rigid body. Let me make a cartoon here to illustrate for you. You remember how, for example, I can take, say, a system of reference and write, for example, here, particle 1, particle 2, particle 3. Let's say this is particle 1, this is particle 2, this is particle 3. I can represent the position vectors of this particle, right? Let's say this is R1. Let's say this guy is R2. And let's say this is R3. 3 position vectors, right? 3 position vectors. I could, of course, have a particle, I could have many particles, and this would be my nth particle, and write the position vector for that nth particle, right? N particle. Look at that. Let's write it like that. That is the position vector of the nth particle. So you already know that I could, for example, if I represented these as the velocity vectors for each particle, right? Look, this velocity vector would be v1. Let's have this other velocity vector here to be v2, and this velocity vector to be v3, and so on and so forth, right? So let's this one over here, let's make this is the velocity vector v3. Let's go over there. This is v1, sorry. So each of these particles have mass. Here's particle m1, has mass m1. Here's particle 2, has mass m2. Here's particle 3, has mass m3. You know that I can write something called the linear momentum of the system. I can write the linear momentum of this system like this. See? If I take the mass m1 multiplied by v1, m1 multiplied by v1, remember I had here particle m1. If I take m1 and multiply by the velocity v1, I'm going to be getting the linear momentum of the particle 1. If I take the mass m2 and multiply by the velocity vector of the second particle, I have the linear momentum of particle 2. If I add them all together, right? If I add them all together, I get the linear momentum of the system. I want you to do something similar with the kinetic energy. Check this out. I want to take the mass of particle 1, multiply not by the velocity vector, but by the speed square. If I take the m1, multiply by the speed square, and put the 1/2 here, you see what this little guy is? You see what this little term actually is? This is the kinetic energy of that particle m1. See? This is the kinetic energy of that particle m1. If I go to I equal to 2, then I get the kinetic energy of particle m2. If I add them all together, what would that be? That would be the kinetic energy of the entire system. The kinetic energy of the system. And I can think of the rigid body as being a collection of many, many, many particles, right? So, check this out. What am I trying to do here? I'm trying to represent my rigid body. Imagine that my rigid body is a body that has many particles. I just wrote m1 and m2 here. But let's put some more. Here's M3. And here's M4. And this big body is going to rotate about this axis. This is the axis of rotation. So I get this body to rotate, to spin, the whole body to spin about a fixed axis. So the whole thing is spinning, is turning. Each individual particle of the rigid body, I can consider it as having a linear momentum and as having a little kinetic energy. If I sum over the entire body, I actually get the kinetic energy of the entire body, or I get the linear momentum of the entire body. It's a sum situation. Now, let's do this now. So each little element of the rigid body has an element of kinetic energy. Now, you know that each of those elements, they were actually doing what? They were actually doing a circular motion. If I take each particle will have a certain position with respect to the origin. But now, because they are rotating together like this rigid body, they all have the same omega. So I can relate the linear velocity of each element to the radius of each element by multiplying each one by omega. And so, look at this expression. This is the expression for relationship between linear velocity and angular velocity. And if I substitute this VI in this expression, see this VI? If I substitute this VI here for omega Ri, notice what's going to happen. I can actually transform this expression for the kinetic energy. Look at that. Half of Mi equal to omega Ri, these things squared. What have I just done here? I've replaced the individual linear velocities by the omega Ri, which is actually what each the linear velocity related to the angular velocity of each one. So this transformation is very important, because notice what I can do now. I can reorganize this expression for the kinetic energy like this. Look, this is a summation of many terms. Now, 1/2 is a constant. It's going to show up in all the terms. I can pull this out of my summation and put it over here. Now, omega is also a constant, because all the objects in the body rotate with the same angular velocity. It is omega squared. I can square it and move it out of these parentheses. And I'm left here in the parentheses with something that I cannot move away from the summation, which is the individual mass elements of the elements of mass in the rigid body and the radius squared. So look at this object that is actually dependent on the index I. We give it a name to that object. Oops, something happened here. We give it a name. You see this object that we are showing here? We actually call that the moment of inertia, or the rotational inertia. So I can write the kinetic energy with I started by simply saying that it is the sum of all the individual kinetic energies of the little masses on the rigid body. I can write it in a compact way as like this. If I just call this complex object, which is a kind of a, it's a type of weighted average of the inertia of the system. You see, it's a sum of the masses of all the elements, but the weight here is actually the distance that they have with respect to the center square. If I call this object I, you see I can represent my kinetic energy by 1/2 of I omega squared. This expression is a very nice expression, because I'm sure you will immediately recognize that it has a similarity with the kinetic energy of translation. Remember, the kinetic energy of translation was like this: 1/2 of m v squared, where this is the translational velocity. This is the angular velocity. Omega is the angular velocity. And what is in place of m here is actually something that has to do with m, but not with m alone. It has to do with the distribution of mass in the object, how the mass is distributed along the several positions in the object. This is called the translational kinetic energy. This is called the rotational kinetic energy. And m is the mass. It's just a scalar, just a number. The moment of inertia is also a number. When you're talking about rotation about a fixed axis, it's also a number. But it's a number that depends not only on the mass, but also how the mass is distributed in your rigid body. So this is a very important concept, the concept of rotational inertia. Sometimes you will see this called as the moment of inertia. See, the moment of inertia or the rotational inertia is a constant for a rigid body because the distribution of mass is fixed, and every little element of mass you can multiply by the distance from the axis of rotation, and you can talk about the rotational inertia of a rigid body for rotation about a fixed axis. Of course, you always have to specify which axis you're going to do the rotation about. The moment of inertia for rotation of this pen about this axis in the center is one number. If you want to rotate it about this axis, then it's a different number. We have to explore that. Very important number, the moment of inertia or the rotational inertia. Let me show you a cartoon of different objects. Any extended object has rotational inertia. What we're going to be doing next time we continue this, we're going to be learning how to calculate the rotational inertia, say, of a wheel, or something as complex of a ballerina. How we would conceptually visualize the rotational inertia? Can we find the rotational inertia of a sphere like planet Earth, for example? And the answer is yes. We're going to be looking at different objects. And notice, for example, imagine a rod, very much like this object. It's much easier to rotate the pen about the axis along the pen than for an axis perpendicular to the pen. And so that's what I'm talking about. The moment of inertia or the rotational inertia for the pen or the rod along this axis is for rotations about this axis is different than the moment of inertia for rotation about this axis. So we have to talk about that. Just to anticipate, for rigid bodies that have continuous mass distribution, this summation will require an integration. It will become an integral. We're going to have to look at that in detail. This is something that you will be coming up when you are working on your next assignments. Look, we have here a system that has mass like this is a square, right? 4 masses. They're connected by rigid rods, and mass MA, mass MB, mass MC, mass MD. Can you find the coordinates of the center of mass? That is something we talked about already in a previous lecture. How do you find the coordinates of the center of mass? You have to use the expression for the center of mass. But also look, find the moment of inertia for rotation about an axis that passes through this A here. What is A? A is an axis for this axis that passes through mass A. It's perpendicular to the page. How hard is it to rotate this object about this? You have to do a summation. How do you do the summation? Take the mass of MA, multiply by the perpendicular distance to the axis. That is 0. The first term is going to be 0. Take the mass MB, you have to multiply by that 10 centimeters square. That's the first element. look, MD have to multiply also by 10 centimeters square. This guy, the distance to the axis of rotation is actually 10 centimeters square root of 2 because it's the diagonal of the square. So this is going to have three terms to figure out the rotational inertia. The rotational inertia is going to be a term that comes from this, a term that comes from that, and a term that comes from that. The same problem is interesting because it asks you later, look, or actually a subsequent problem. What is the rotational inertia for rotation about this axis? Now we're talking about rotation about a different axis. So it's what it counts here is what is the distance of this mass to this axis. That is what should go in here. One term. What is the mass? What is the rotation for this mass? I'm sorry. What's the distance of this mass to the axis of rotation? It should be this half diagonal from here to here. Square times its mass. Add this term with that term. You have two terms in this rotational inertia. You see that these two contribution will be zero because they're right on the axis. Their distance, their perpendicular distance to the axis is zero. So we're going to study rotational inertia of more complicated objects. But these two examples that will come up on your assignment will get you started on how to evaluate the rotational inertia. So we're going to stop here for the time being on this area of rotational introduction. So what did we do? We introduced the kinematics of rotation. You have to understand what is the angle, what is the linear speed, what is the angular speed, and also what is the corresponding accelerations. Then you have to begin understanding some of the energetics, which is rotational inertia. Why? Because this is very important when we write the kinetic energy. The kinetic energy of rotation, again, very important message to take away from this lecture. The kinetic energy of rotation is actually equal to 1/2 times this guy, the moment of inertia or rotational inertia, times the angular speed squared. So any object that is rotating will have a kinetic energy of rotation like that. If it is translating also, it will also have an additional kinetic energy of rotation. So let's stop over here, and next time we'll continue with the introduction of the idea of the angular momentum, which is a next thing that we need to talk about for rotational motion. Thank you.